Alright guys, so this is a overview for the Linear Regressions Chapter 8 for AP Stats. So before we get started, like I just said, this is an overview, so it's going to go over the main points that you should have gotten out of the reading, sorry. And also it will be a good study aid for when you get to the AP Stats test, or the weeks leading up to studying for it. A lot of this stuff is on the AP Stats test, so make sure you pay attention to it keenly, just as you would everything else, though. So let's go ahead and get started. So while reading this chapter, keep these objectives in mind. So 1.12, the student will analyze patterns and scatter plots. 1.13, the student will assess the linearity of bivariate data. 1.14, the student will calculate the coefficients of correlation and determination. 1.15, the student will determine the equation of least squares line. 1.16, the student will make predictions using the least squares regression line. 1.17, the student will analyze residual plots for patterns. And 1.18, the student will analyze the effect of outliers and influential points on the least squares regression line. So if you've read through the book already, you'll understand what some of these things are, and also how they go into being able to do the linear regressions. So these are just the main points that you should have gotten out of the reading, what you should have learned. Of course, it's a little bit more in detail about certain things in the chapter, but like I said, if you're reading, then you'll understand what's going on and also how this relates to everything. So what you should have learned about in Chapter 8, we have all the different sections of the book in Chapter 8. So go ahead and get started with residuals. So residuals, or predicted value, is the estimate made from a model y hat. The difference between observed value and its associated predicted value is called a residual. Residual values tells us how far off a model's prediction is at that point. To find residuals is observed value minus predicted value. So again, just the main points of that section of the book. Alright, then least squares. So best fit means least squares. When we draw a line through a scatter plot, some residuals are positive and some are negative. Squaring the residuals makes them all positive. Now I can add them up to assess how well a line fits. Squaring also emphasizes the large residuals. The smaller the sum, the better the fit. The line of best fit is the line for which the sum of the squared residual is the smallest, the least squares line. So that's where that comes from, the least squares line. And also, when this line is fit, you want it to be best fit, so that's what you'll put in like a calculator. When you're going into doing the math, it's a best fit. So what this means is that basically the predicted line is the best fit to your actual data that you'll be fitting this line to. So that's where the squares come in, is that you want to be least squares because then the line is closest, the prediction line, the predicted line, is the closest to your actual data as it can be, the least squares line. So correlation of the line. So recall, equation for a line that passes through the origin can be written with just a slope and no intercept. So y equals mx. Coordinates for standardized points are written as z-scores. So z hat y equals mzx, and the best choice for m is a correlation coefficient itself, r. So z hat y equals rzx, and this is the final equation. This equation tells us that in moving one standard deviation from the mean in x, we can expect to move about r standard deviations away from the mean in y. So again, just using these equations to find out what your best choice is for the coefficient and all that, trying to figure out the math and figure out the line and how it will fit. Predicted values. So it says how big can predicted values get? They should be no more than 2 standard deviations away. Each predicted y tends to be closer to its mean in standard deviations than its corresponding x was. So this 2 standard deviations away applies to a lot of chapters for doing models and linear regressions. So this is because of what percentage 2 standard deviations covers on a normal curve. So that'll be, I don't know if you've learned about that so far, the chapters previous, but like I said, the 2 standard deviations away is pretty much the same throughout the whole book, I should say. So this is a rule that you won't ever forget. You shouldn't forget. It's one that will be used a lot, not in this chapter, but in a lot of other chapters also. So, residuals revisited. So, data equals model plus residual, or residual equals data minus model can also be written that way. E equals y minus y hat, same thing. So a scatter plot of the residuals versus the x values should have no direction or shape, stretch horizontally with about the same amount of scatter throughout, show no bends, and not have any outliers. So the two biggest ones in this one are the having no direction or shape and also showing no bends, because as you see on this next bullet point, if any of the above features found, find out what the regression model missed. So if you have a shape or you don't have random scatter, it'll be something is wrong and you want to make sure you look at it. So then residual standard deviation. So the standard deviation of the residuals, SE, gives us a measure of how much the points spread around the regression line. The points should all share the same underlying spread. Equal variance assumption. The residual plot has the same amount of scatter throughout. Does the plot thicken? Condition. So SE equals the square root of the sum of E squared divided by N minus 2. So this seems like this seems wordy, but once you start doing this, you'll understand how it actually relates into the linear regressions, and it actually helps a lot because you have to check those conditions before you can definitely say, yeah, this will work. So R squared variation accounted for, how big should the R squared be? So we'll go with the R squared variation accounted for. So comparing the variation of a response variable with the variation of residuals, the squared correlation, R squared, that's a little r, gives the fraction of the data's variation accounted for by the model, and 1 minus r squared is the fraction of the original variation left in the residuals. Because r squared is a fraction of a whole, it is often given as a percentage, and you'll see this a lot throughout the book also. How big should r squared be? So R squared is usually between 0% and 100%. Data from scientific experiments often have R squared in the 80% to 90% range and even higher. Data from observational studies and surveys often show relative weak association, 50 to 30% or even lower. And also the answer to this depends on what kind of data you're analyzing and on what you're doing with it. So of course, it's always situational. You have to look at what you're doing and really what that R squared should be. R squared of 100% is a perfect fit with no scatter on the line. The SE would be 0. So again, just looking at that value, making sure it's not too big. Assumptions and conditions for regressions. So quantitative variables condition, of course, no categorical variables. Linearity assumption, relationship with variables is linear. Straight enough condition, not perfectly straight, but straight enough for model to make sense. So this is an interesting one because this actually takes into account inference. So this is like, it's what is an opinion based on what you've learned. So this could be different for two different people. It's kind of weird. I know a lot of an AP stats is a inference based. Basically, what do you think based on what you've learned? Is it straight enough for what you're doing? Equal variance assumption, all residuals should share the same spread. Does a plot thicken condition? Again, checks for changing spread. Outlier condition, checking for outlying points. So again, you have to meet these conditions to do the linear regression, or else you won't be able to do it. It won't work. So this is just checking in the book. So it says, back to a regression of house price in thousands of dollars on house size in thousands of square feet. The R squared value is reported as 59.5%, and the standard deviation of residuals is 53.79. Before I go any further, I wanted to correct myself on the slide. The little r should actually be a capital R, and there is a difference in how it's written. So continuing, 11, what does the R squared value mean about the relationship of price and size? So this is going to be from the book. This is one of the examples. 12, is the correlation of price and size positive or negative, and how do you know? So this is again an inferential thing. You have to write down what you see and how do you know that the correlation of price and size is positive or negative. If we measure house size in square meters instead, would R squared change? Would the slope of the line change? Explain. And then 14, you find that your house in Saratoga is worth $100,000 more than the regression model predicts. should be very surprised as well as pleased. So again, this is taking into consideration that the least squares and looking at what this means for each individual situation. So then, back to the table of contents. What can go wrong? So these are the things that can go wrong if you do something wrong with this, or if it's not, you don't meet the conditions. So don't fit a straight line to a nonlinear relationship. That will cause a lot of issues, and you won't be able to use it. Beware of extraordinary points. Again, this is going to throw off that least squares regression line. It'll pull it up or down, or skew it. Don't extrapolate beyond the data. So this is a really big one. A lot of professionals do this for predicting values, but really, because there are so many different variables that go into the data and how it's gotten, and also trends in the social and economic world, you don't want to extrapolate beyond the data, because something extreme could happen and make the values go up or down at any point. Don't infer that X causes Y just because there's a good linear model for the relationship. So again, this goes against everything that you say in your mind. You think, oh yeah, because X is doing this, that's what's causing Y to be this way. And you can't do that, because there's actually, like I said, there's other variables that go into X and Y being what they are, and it's not just X is changing or Y is changing. Don't choose a model based on R squared alone. So you have to look at all of it. You can't just look at one part of the model. So then we'll go to the homework. So it's page 192 to 193, questions 1, 3, 5, 7, 9, 11, 15, 16, and 18. So it seems like a lot of problems, but they're pretty simple. They're not too bad, and this is really what you should be able to do. You should be able to do all the problems, but these are really good ones to, first of all, for starting out, and also for a little bit deeper knowledge into the chapter, and being able to make sure that you understand everything you need to know for the AP exam. And really that's what you're trying for right now, is you're trying to just get to that AP exam, trying to pass it, and really do good in the class. It's really hard to do well in the class if you don't read the book. And then vocabulary. Just kidding. Go back. So sorry about that. Vocab. So model, equation, or formula that simplifies and represents reality. Linear model, equation of a line, predicted value, value of y hat found for a given x value in the data, found by substituting the x value in the regression equation, values on the fitted line. So residuals, differences between data values and the corresponding values predicted by the regression model. So residual equals observed value minus predicted value, or E equals y minus y hat. Least squares, unique line that minimizes the variance of the residuals. Regression to the mean. Each predicted y hat tends to be fewer standard deviations from its mean than its corresponding x. And a regression line / line of best fit is y hat equals b0 plus b1x. So these are the different things that you should be looking at and be able to do. And that is the end of it. So basically, being able to do all this will help you get through the chapter.